Well, going back, we looked at exponential functions, like e to the x, e to the x, and we looked at log functions. And we learned a bunch of rules for manipulating exponents and logs. And now we're really going to put them to use. The subject today is 4.5 in the book. Exponential and log equations. I don't know. So we're going to have to solve some equations that are going to have exponents or logs in them. And before I say anything about that, I want to reiterate something I said. I think the first day I talked about logs, which are that log and exponential functions are inverses, inverse functions. In addition to knowing that they're inverses, you should know all inverse functions are one-to-one functions. And that'll come in handy in a minute. 2-1 means they pass the horizontal line test. They only go through each y at most once. All right. Here, I'm going to just do something really simple here. I have something like x plus 3 equals 5. So everyone knows how to solve this. But I want you to think about something very fundamental that's going on here. Well, of course, we're going to add minus 3 to both sides. What is adding 3 to 3? What we have is an inverse function. You add 3 to something, you subtract. So the way we isolate x here is we use this feature that there's an inverse function. We've been doing it for so long and so naturally, we may kind of forget that. Well, that's the same strategy we're going to use with these exponential log functions. All right. So we'll come to that. So let's start with just something very simple. I have a to the x equals a to the y. Because these are one-to-one functions, I can immediately assume x equals y. There's even a more general, you don't need to know this, a general idea. If f is a one-to-one function, then f of x equals f of y implies x equals y. That's true for any inverse. Similarly, if I have a log function, log to the base a of x equals log to the base a of y, I can conclude that x equals y. So this is going to give us some strategies for solving some of these equations. You can make this direct association, but you also can do some calculation to do this too. You could say a to the x equals a to the y. If I find the log to the base a of both sides, log to the base a to the x equals log to the base a to the y. Well, this is x log to the base a of a equals y log to the base a of y log to the base a of a. You might recognize this identity here as being 1, but regardless, we can divide it out and we get to x equals y. We can do the same thing here with a log. We can raise both sides to a. We could say a to the log the base a of x equals a to the log a of y, and recognize this identity, a to the log a of something, is just that something, and the same here. So these are kind of strategies or tricks or, I don't know, methodologies to actually solve real equations that we're going to look at. So we'll start simple. We'll start with something that you probably can see the answer to without resorting to this. We're going to say 5 to the x equals 125. You don't need to take this class to have figured out that this is 5 times 5 times 5, so x is going to be 3. But a more methodological way would be to say, all right, well, let's write that as 5 to the 3, and I can immediately see that it concludes x equals 3. Another way to go about this would be to say, well, I've got an x as an exponent, how do I bring that down? I can find the log, right? So if I find the log to the base 5 of 5 to the x, so that's log to the base 5 of 125, well, that's just x over here. And now I just need to know how to figure out what log to the base 5 of 125 is. Of course, again, is 3. So that's a simple example. All of what we're going to do here in this section is use these kinds of strategies to get us to equations that we should recognize from algebra and from earlier in the class, things we've already learned how to solve. All right, again, moving slowly here. I have 5 to the 2x equals 5 to the x plus 1. Well, initially that looks quite ugly and scary, but again, we can immediately assume from this that 2x equals x plus 1, an equation we know how to solve quite easily. Right? We just subtract x and we get x equals 1. Things will get more difficult, but not terribly so. We might not have something nice and clean like this where we're going to get a nice pretty answer, but we can still use the same strategy here. All right, we'll look at that and go, how are we going to come to a solution to that? Well, using the strategy I used over here, let's find the log to the base 3 of both sides. All right, this becomes x plus 2. Oh, that's fine. I mean, this is just a number, right? You can leave it like that for the moment. There's no reason to try and reduce it. It's not going to be a very pretty number to look at. So this is just x equals log to the base 3 of 7 minus 2. And that would be a perfectly good exam answer. You could, if you wanted to, if you're doing some science experiment, you might want to convert log to the base 3 of 7 into a log to the base 10 value, because then you can use your calculator and get a number. So if you recall, log to the base 3 of 7 is going to be log to the base 10 of 7 divided by log to the base 10 of 3. That's just, that nice conversion of base formula that's useful. It's kind of too bad the calculators don't come with that built in. Can raise any value to a power, but you can't find any arbitrary log, but you can use this formula. All right. Take a breather here for a second. Catch my breath. Any questions so far? Is this completely new to anybody? I mean, working with logs and equations? Okay. Again, there's going to be some homework problems. You'll get a little practice. And, this is just very, very useful general math that you might run into in another science class. We do use logs to some degree in computer science when we're trying to think of the right term. Anyone run into big O notation? You're trying to figure out if some algorithm is better than some other algorithms. You have to compare how they scale. And sometimes I don't mind drifting a little here. Let's say you're a computer scientist or you're some person who has a bunch of things you want to sort. Some numbers. And you have a list of them and you want to know, well, how do I sort these? Well, one way is to go through and say, all right, is 3 less than 4? Yeah. 4 less than 5? Yeah. Is 5 less than 7? Yeah. 7 less than 2? No. Switch them. Is 7 less than 1? No. Switch them. So now you know that the last item in the list is in the right place. So you go through the list again. Is 3 less than 4? Is 4 less than 5? Is 5? Oh, 5 is not less than 2. Switch them. And you keep doing that n times. This is called bubble sort. And we would call this big O n squared, meaning if you have a really big data set to sort, like a million, it's going to scale as, a million squared, which means it's not very efficient. Now, I'm not teaching computer science, so I'm not going to go into the details, but if you're a computer programmer, you'll usually have this thing called quicksort available to you. And how does it scale? It scales big O n log n, which is much better. I mean, every time you add something to your set, of course it makes it a little longer, it takes a little longer. But instead of n squared, it kind of tapers off. N increases, but it kind of it's like this. So as you get into a really big set, it's heading towards just scaling as n. So, all right. Random interleaved. So getting back to what I started with, saying, you know, we're gonna be doing things the same way we solve other algebraic equations. We isolate our x somehow, and we use the fact that we have inverse functions to remove these exponential and log functions. So, as an example, let's take a e to the 2x equals 20. So we're working our way to get this x isolated. And the first part of it should be straightforward. We do this all the time in algebra. You just divide both sides by 8. So we get e to the 2x equals, what's this? 2.5. It's 5 halves. All right, now what are we going to do? What would be the next step to get to this x? Any thoughts? Guesses are okay. Yes, Rachel?
Can you make E L N? Is that
Like this?
not?
Why not?
I wasn't sure that was right.
Take the ln of both sides. This is going to become 2x. Remember, I just took the inverse. All right, 2x equals ln of 5 halves. Now I have x equals ln of 5 halves over 2. Which again, if you want a decimal number, the calculator can give you that. We could have something a little more complicated. We could have, say, e to the 3 minus 2x equals 4. Again, we're going to just take the ln. And again, you know, by taking the ln of this function, they're inverse functions, so we just end up with 3 minus 2x. From here, this is, you know, again, this is just a number. You don't have to worry about its value. We can just solve for x. All right, minus 2x equals minus 3 plus 4. X equals minus 3 plus 4 over minus 2. Which again, if you want a decimal number, you can use your calculator. Right, things can get trickier. Here we have something where isolating x will not be that simple. What am I going to do with that? Well, you want to notice that this is e to the x squared minus e to the x minus 6 equals 0. Looks suspiciously like a quadratic equation. So let's make a quadratic equation we need to solve. Let's just say that y equals e to the x. We'll deal with this later. And we have y squared minus y minus 6 equals 0. Well, we know how to solve that. We can factor it, or we can use the quadratic formula. Let's try this. It's either 6 and 1 or 3 and 2. 3 and 2 differ by 1. So it's going to be y plus 2, y minus 3 equals 0. So we get y equals minus 2 or y equals 3. Then we have to go back, right? dx equals minus 2 or dx equals 3. All right, in both cases, we can try and find the ln of x. ln p dx equals ln minus 2, ln p dx equals ln 3, and this just becomes x. But we have a problem here. Does anyone see the problem? This is fine. The log of 3 is perfectly well defined, I think. What about log of minus 2? Anyone remember the domain of the log function? Typical log function looks like this. These values, negative and 0, are not part of the domain. So this is just a spurious solution. It's not a real solution to this. But something to keep in mind with these problems. Occasionally you'll get these, I guess, I call them phantom roots. They come out of solving the equation, but when you plug them back in, they don't make any sense. All right. Sometimes things are not so hard, even though they might look it. If I had an equation like this, 3x e to the x plus x squared e to the x equals 0, that's going to be problematic, isn't it? E to the x times two different quantities, and just solving for this x is not going to help us because there's other x's. How do we go about this? Well, it turns out this equation is quite easy. We're just going to fall back on something we've beaten to death. It's just, let's factor this. This is equal to 0. Let's factor it and see what the factors are. So we get x times, I guess e to the x is a factor. So we have 3 plus x equals 0. That theorem of algebra tells us if the product of some things are 0, then if any of them individually are 0, they're a solution. So immediately we can see x equals 0 is a solution. This tells us x equals minus 3 is a solution. What about e to the x equals 0? Well, Well, you could just jump right in and say, hey, there's no way to get 0 raising e to some value. If you have a negative value, it's a small number, but it's positive. If you have a positive value, it's positive. Excuse me. And if it's 0, it's just 1. So, no solution here. I think I'm going to go get a drink of water, so we can take a break for a minute. Mostly we've been looking at equations that have exponential functions in them. Same kind of strategies are going to work with log functions, however, dealing with logs is a little different. You just have to remember our rules for handling logs. So, I have an equation like this. What am I to do with this? Well, I can't just say this is x squared plus 1, x minus 2 plus x plus 3, because it doesn't work that way. However, I can simplify this, right? The log of x minus 2 plus the log of x plus 3 is what? What are the laws of logs? Tell me about that. Log of a plus log of b is log of what? A times b. So that works equally well with this. Now I can get rid of my logs entirely. X squared plus 1 equals x minus 2 times x plus 3. Working this through, we get x squared minus 2 plus 3 plus x minus 6. X squared is canceled. So we get x equals 7. We want to check the answer. We want to make sure this actually is valid. So what do we have? We have the log of 50 equals the log of 5. That's the log of 10. That looks right, isn't it? 5 times 10 is 50. You could find it, you you plug in your solution and you get a log of a negative number, which is fun to find. It doesn't work. I somewhat recall a few weeks ago making a big deal out of the idea that I had something like e to the a equals b. Guess I want to write it here. B equals a. And b is going to come out in the right place. I can always rewrite this as log to the base b. No. This is the base. On to the base e, a is equal to b. All right, you can switch between those forms. Well, that could come in handy if you have a problem like this. Limit of x equals 8. I switch that. What do I get? I get e to the 8. E to the 8 equals x. That's a simple example. If I have something like this, log to the base 2 of 25 minus x equals 3, okay, it would be convenient to say, all right, that's just what? 2 to the 3 equals 25 minus x. Oh, well, that's a nice, easy problem now. Because this is 8, and we just have some nice numbers here to solve for. So we have some strategies here. I think the next step is to not panic. All right? I see something like this. A lot of stuff here. I'm going to get to this 2x. Well, just use the skills you have with algebra and step by step get to where you're just left with x. So, of course, you subtract 4. Divide by 3. And you just, break it down piece by piece until we get something we really do have to think about. Okay, so again, we can write this in the other form. That would be 10 to the 4th equals 2x. X equals, this is 10,000, so it's 5,000. Now that's going to take care of most situations you're going to see in a math class. In the real world, sometimes things don't work out nicely, nice and clean, and you have to resort to other methods. I have an example here. Suppose you're doing some kind of analysis and you find yourself in this kind of ugly equation. Well, that's really unfortunate. Yeah, x over here is part of the log, and by itself even. We have x squared over here. Well, we give it a try, right? So maybe we bring the 2 over here, and we're going to switch this. I guess we could do it by raising each side to e. And where do we end up with e? X squared over 2 equals x plus 2. Oh, so that didn't help much either. The problem is our x's are separated this way. And we don't really have a good analytical method of doing this. However, we're not out of the water here. We're going to bring up a tool that you might have available. You can also do this on a TI calculator. Wait for the projector to come on. So you'll notice on the left, I'm graphing the left side of our equation, and on the right, below I'm graphing the right side. And we see, in fact, there are two curves, and they do intersect at 2 different points. And the Desmos can go over, get an approximate value, 0.507 here is one of the solutions. I'm sorry, 0.507 is the value of x squared. Negative 0.712 is the x value. Down over here, you can see it's 1.601. So, in a pinch, you can at least get an approximate value for something like this, where we don't have a direct root. You might want to try and use your TI calculator to do essentially the same thing. I will give you a hint. There's a calc feature called intersect. It's going to apply on the calculator. I've never gotten it to work. However, it seems redundant. What you can do here is you can write it this way. X squared equals x squared minus 2 and x plus 2. You can enter this as some function. And you can look for the 0. Because wherever there's a 0, you're going to have a solution. All right, one more practical example. example of this from business, or I guess we could call it banking. Problem is, you invest $5,000. Why would anybody like to have $5,000 in their pocket today at a rate of 5% interest? And they want you to find the time required to double your money. So you could say P of 0, that's the principal, is 5,000. And then P of T, some time value, is 10,000. To make things difficult, the problem is two ways, either compounded semi-annually, two ends, or how do you call it? But also continuous. So first, semi-annual, what does that mean? That means that the bank, like, after 6 months, gives you some interest, and then after 6 months after that, they give you interest on the money and the interest. So what does that look like? We're going to use Y for, instead of time, years. So we have our initial $5,000. 1 plus, well, 5% interest semi-annually is half of that, right? So half of that is 0.025. Just write it 5% over 2. And we needed 2 here because we're doing it twice a year. And we want that to be equal to $10,000. Right, so we have P0 is 5,000. So let's divide 2 by that. Well, now we have an exponential function here, right? What are we going to do about that? Yeah.
For the initial, which is 5,000, we're dividing that into 10,000, or are we
Oh, yeah.
subtracting? I mean, the
Did I mention I'm going to make a lot more mistakes today than usual? Yeah. Thank you. Okay, so what do we do now? We want to find what y is, right? It's in years. We want to know how long does it take to double our money. This works equally well if you just say double your money. It doesn't matter that it was what you start with, does it? Well, what have we been doing when we have an exponential function with the variable in the exponential function? We can either rewrite this in the log form, or we could find the log of both sides. It's going to give us 2y log of n plus 5 over 2. Log of 2. And now we can just solve for y. You'll note that I just said log, I didn't say log to the base 10 later. Since we divide out, it's going to not make any difference. All right, that's compounded semi-annually. You can adjust that for how often you're compounding it. With continuous, the formula is a little easier. E of y is E0 into the 0.05y. That 0.05, that's the interest. So again, we have 10,000 here, 5,000 here. Through, and we're just trying to find e to the 0.05y equals 2. And how would we get a little further? This is your money here, right? It's growing, right? Sides, this becomes 0.05y equals 2 divided by 0.05. Takes 13 years. All right, that's all for exponential and log functions. As I said, it'll be a homework assignment. Get some practice, and we will be ready for whatever comes. So why don't we take a 5-minute break, and then we're going to be on to something new. We're going to start now on the next major section of this class, the last section. It's going to take us to the end. The subject is trigonometry. And I'd like to ask, is there anyone who has has never done any trigonometry in high school or anywhere? Okay, we've all seen some of it, so hopefully when we get to the meat of it, it won't be all new. But we're going to go into it in maybe a different manner than you've seen before, maybe not. start with talking about something called a periodic function. And we have a formal definition. A function is periodic if for all x in the domain, there's some number p where f of x plus p equals f of x. What does that mean? Well, you can think of this lots of different ways. If you think of a clock, as the value of a clock being a function, every 12 hours, you get the same value. It's not just at 12, any particular time you might pick. 12 hours later, it's the same time. So that's what this definition means. Now, this P is not unique. See, I can come back in 12 hours, or I can come back in 24 hours, 36, 48 hours. So, some texts will call P, a period of the function. And I forget what how our text refers to it, but if you take the smallest p, that's the period of the function. Obviously, it's the period. So that's the smallest p. Whenever you have a p, you can always multiply it by a factor and you still get another period. So what are some examples? I mentioned the clock. You go down to the beach, you watch the water come in and out. You have high tide and low tide. That's a periodic function. You look up in the sky and you look at the sun. Where the sun is above us, that's a periodic function. You look at the moon, same thing, except a much greater period. Many periods that we deal with in science or in general are periods of time. But not all periodic functions have that. I'm gonna bring up the screen now. We're gonna just take a look at a few examples of periodic functions. Since you've all run into trigonometry at some point, I won't have to explain. We're going to go into a lot of detail, but I won't have to explain that there is such a thing as a sine function, which itself is periodic. It repeats every 360 degrees, or if you're familiar with the radian measure, which we'll get to, every 2 pi. The same with the cosine function, which looks suspiciously like the sine function. It's actually the same curve, but moved over, and we'll get to that. We call that a phase difference. Likewise, we have the tangent function, which doesn't look like the sine and the cosine, but it does have it repeats. Now it's repeating every 180 degrees, or every pi radians. It's not defined in certain locations, but that's periodic too. I don't think we have any, I don't recall any electrical engineers in here, but if you've ever played around with an oscilloscope and a signal generator, you might have seen these types of periodic functions. First, it's called a square wave. All your computers have a clock. It's a little electric circuit that produces a square wave. It's not a perfect square because to be perfect, you would have to jump from a high voltage to a low voltage instantaneously, but it's pretty quick. You can also you can have what we would call a triangle wave or a sawtooth wave. And these are all part of electronics to deal with. I can't think of any other applications of these periodic functions. But again, you see, as long as you're a distance of the period, the value is always the same. It's just the same idea. Okay, from astronomy, we have the rotation of moons around, in this case, Jupiter. Jupiter has a number of moons, and you can see they all kind of have a periodic, different period, but a periodicity to them. So periodic functions are part of the natural world, and we're gonna study them a little bit. Sunspots. Well, most people can't really see sunspots without a proper telescope and filter. You can see two periods here. Every approximately 11 years, you have a peak. And then the peaks themselves will vary, although it's not a very nice period. You see, you have increases and decreases of sunspot activity. A lot is known actually what causes this. It's not precisely known, but it has to do with the magnetic field of the sun. Kind of gets wound up tighter and tighter, creating these sunspots are actually a cool spot on the surface of the sun. And the magnetic field actually causes some cooling. They're still very hot, but they look darker. And then every 11 years, for, I believe, still unknown reasons, the magnetic field switches. I think that's also true of the Earth's magnetic field. It switches periodically, but it's over a much longer period of time, hundreds of years, and we're apparently approaching a period when the magnetic field of the sun will switch. I don't think it's in our lifetime. And this is just a graph of the tides off of the New York Manhattan coast. And you can see over time they vary. They'll also vary they'll also have another period based on the time of the year, which has to do with where the sun is and the moon and so forth. Okay. So I have a little 2-minute video here. I hope this is entertaining. I hope there's sound, I'm not sure. We'll see. No, I don't seem to have sound here. There's something. Let's try again.
Ultimately compressing and expanding it with each vibration. The variation in sound pressure can be detected not just with your ear, but also with a microphone connected to an oscilloscope that traces out a sine wave, showing how the sound pressure varies with time. We can also make sine waves with an electronic synthesizer. The number of vibrations per second is called the frequency. It's related to the sound or tone. For example, this tone has a frequency of 440 vibrations per second. Here's what happens if you double the frequency. The new sound, an octave higher, is called an overtone. And here's what it sounds like if you cut the frequency in half. The new sound is an octave lower. The height of the curve, up or down, depends on the loudness or intensity of the sound. The maximum height of the curve above the axis is called its amplitude. These examples show changes in amplitude for a given frequency. More complex sounds can be made by combining sine waves. For example, if you combine this tone with this overtone, the graph of the combination is obtained by adding the corresponding heights of the two sine curves. It sounds like this.
Okay, so I know maybe there's some pianists or instrumentalists out there. I find this interesting. You play a tone on an instrument, different instruments will sound differently playing the same tone because they have different overtones that he was talking about, different combinations of them. All right, so just a few quick definitions here. You have a periodic function. Say some f of t. We define the amplitude as the maximum of f of t minus the minimum of f of t over 2. You have kind of a sine wave. Doesn't matter where it is with respect to the axis. If you take the maximum and the minimum, it's half that amount. That's the amplitude. Now here's something even confuses me. I have to kind of think this through clearly. So we have a period. I guess I'm going to redraw this as a more standard sine wave. So period is, the smallest period, the period. This is sometimes called a cycle. And its units are cycle is just, I'm sorry. This will confuse me at times. We have something called frequency. Which we're going to use even if the periodic function is not time-based. But for a time-based signal or function, the frequency is, units are cycles, typically per some unit time, say second. So that would be, the amount of time it takes for the signal or the function to get from the starting point to where it's going to repeat. That's its frequency. And its range is just the same definition for other functions. It's, the maximum through the minimum. Since it's repeating, you can just find a maximum and a minimum. Okay, so those are just a few definitions of periodic functions. We're going to look at some periodic functions, and I don't know if there may be some homework problems which discuss some of this, but it's not clear. All right. Any questions about periodic functions? Okay, the next section we're going to look at is on this subject of trigonometry. And I should mention that I'm not doing this in the same order as the book. I really don't understand why the book does it in the order they do, but they do. It doesn't seem very progressive to me. The first place we run into trigonometry typically has to do with triangles. And so I want to take everyone back in time a little bit to, I'm sure it seems like the distant past when you took a geometry course. And I want to remind you of some things we learned in geometry. There were a few triangle equality, or triangle congruence theorems. Does anyone remember any triangle congruence theorems? I'll give you a hint. Most of them were just 3 letters.
SAS?
Sorry. Hold that thought, yes.
Is there like side?
Okay, that's one. Side. You were going to tell me another?
Side, angle side.
Side, angle side. Good. Anyone remember any other? There are a few of them. Not that many. Okay. Well, that's all right. It's been a long time. There's angle, side, angle. There's one more important one. I want everyone. All right. Before we get there, let's at least talk about what these mean. Side means if you have 2 triangles, call this A, B, and C. And another triangle, little a, little b, little c. Little a and big A are the same length, little b and big B are the same length, and little c and little c are the same length. It's a congruent triangle, has exactly the same dimensions. Side angle side says, well, if you have two sides, say A and B, the angle between them is the same, and again you have a congruence. As soon as you have a congruent triangle, you know that all the sides and all the angles are the same. Again, angle, side, angle, two angles and a side with the side between them. And then there's one more special one called HL. Does anyone remember HL? Anyone remember what that stands for? Okay, it's been a long time. It only refers to a right triangle. A right triangle, we have the longer side is the hypotenuse, and the shorter sides are called legs. So hypotenuse leg says if you have two right triangles, their hypotenuse are equal, and one of the legs is the same, and they're also congruent. All right, now there's one more theorem from geometry that we want to look at, which has not to do with congruent triangles, but similar triangles. Similar objects are objects with the same shape. So if I have one triangle, and we call it A, B, C, and possibly smaller, larger, or the same size A, B, and C. And we know that the angles that they share the same measure angles. We call these similar, they're the same shape. And there's some important results from that. Specifically that the ratio of the sides are equal. So, for example, A over A will equal B over B equals C over C. There are other ways to write this. You could say A over B, big A over big B equals little a over little b. So you have all these relationships. Out of these ideas is where trigonometry kind of explodes. So, right, if you don't know these, you might want to, if you don't remember these, you might want to jot them down and think about them. They're not going to go away, either in this class or at least the ideas will not go away. You may not need to do some geometric proof with them, but it's good to know. And I'll try and point out where these things come into play here. All right, so with trigonometry, we're going to start with a right angle. I want to draw it a little nicer. Feel right. This symbol, of course, means a right angle. And another one of the angles, not the right angle, which we're typically going to use the Greek letter theta. And we're going to specify names for the parts of the triangle. Hypotenuse we're just going to call H. the side opposite from our angle, we're going to call O or opposite. I'm not going to spell out hypotenuse. And for the side next to the angle, adjacent to it, we're just going to use A. Adjacent. And we're going to define, for starters, three functions of the angle. First being the sine, and then you're going to see the most of the angle. And we define that as O over H. I want to be clear on why we can do that, right? It doesn't matter what size the triangle is. Any right triangle with a right angle and an angle of theta is similar to every other right triangle with that angle of theta because of HL. Because they're similar, the ratios of their sides are the same. So this is just the ratio of the side, in particular the opposite over the hypotenuse. We go on and we have the cosine, which is the adjacent over the hypotenuse. And we have the tangent function, which is the opposite over the adjacent. Now this refers specifically to triangles. We're going to extend this in a later class, but for right now, this angle, because it's an angle of a right triangle, can only be, well, it has to be greater than 0 or it wouldn't be a triangle, but it also it has to be less than 90 degrees. Otherwise, these would be parallel and we wouldn't have a triangle at all. This definition is so important that over time, educators have come up with a mnemonic to remember. I don't know, it's not the best mnemonic I've ever been trained to. It goes Soka Toa. So you just kind of want to chant that to yourself in your sleep. Soka Toa. Sine is the opposite over the hypotenuse. Cosine, adjacent over the hypotenuse. Tangent, opposite over the adjacent. So anyone not heard that mnemonic before? Is that pretty, everybody learned that at some point? Okay. Yeah, it's useful. All right, so you of course know that on your calculator you have these functions. So you can say, well, knowing that, being able to get a value for these functions, what kind of problems can we solve? So, for example, if I have a right angle with a hypotenuse of 10, and there's a 60-degree angle, I can find the sides of the other angles. That's the sides of the other sides of the triangle. How am I going to do that? Well, this is the hypotenuse, this is the opposite, this is the adjacent. So, if I want to find the opposite, I want to find a function that uses the hypotenuse and the opposite. That's the sine. Here is 60 degrees. That's the opposite over the hypotenuse, which is 10. Well, I don't know. It's O, not 0. And now I can just solve this. The opposite side is 10 times the sine. If I want to find the adjacent, I'm going to do something similar, only I'm going to use the cosine because it involves the adjacent and the hypotenuse. So This is a nice system for solving right triangles. I should point out that because this is just, part of being a math student, that a number of angles we kind of automatically know the sines and cosines of. Spoke about these at the beginning of the class as special triangles. So if you have a 30, 60, 90 triangle, if the hypotenuse is 1, the shorter leg is a half, and the other leg is square root of 3 over 2. So what's the sine of 60 degrees? Just the opposite over the hypotenuse, so it's square root of 3 over 2. Similarly, the cosine of 60 degrees is going to be a half. The tangent, 60 degrees, is going to be opposite over the adjacent. So square root of 3 over 2 over a half is square root of 3. So these are sines and cosines you should actually know the exact value of. The other, well, I'll leave this for the time being. You can immediately see where we get that idea of sine and cosine if you look at sine of 30 degrees. Because that's going to be a half. Cosine of 30 degrees is going to be square root of 3 over 2. And the tangent of, doesn't really enter into this, is going to be 1 over the square root of 3. So you can see that, what's the relationship between 30 and 60? What kind of angles are they? What do you recall? A plus B is 90 degrees. These are complementary. Yeah, all that geometry I forgot. In case it comes up, A plus B equals 180 degrees, and we'll call what that's called. Yes? Supplementary. Not going to spell it. So, sines and cosines of complementary angles correspond. That's where probably the code comes from. All right. There's another set of important angles. They're, as it turns out, much easier. Have what we call an isosceles right triangle. Isosceles meaning two sides are the same. Does anyone recall what the angles for this triangle are? Yeah, this is pretty basic. 45 degrees. Well, that's nice. That means the sine. Well, let's get this. If this is 1. This is this 1 over the square root of 2. 1 over the square root of 2. You can kind of find these relationships using Pythagorean theorem, right? A squared plus b squared, that's 1 over the square root of 2 squared is a half, plus a half is 1, right? So the sine of 45 degrees and the cosine are 1 over the square root of 2, and the tangent These are all important angles that you should commit to memory, because they're going to come up that often. All right. I want to do a kind of like a tech commercial here. Anybody who has their calculator with you, I'd like you to at least take it out and look. Maybe show it to your neighbor. And I want you to, once you get it turned on, I want you to click the mode button. Everybody, can you see that? So if you look 2 lines down, you should see something that says radian and degree. Anybody not see that? Who has their calculator? Okay. Exams are failed or passed, depending upon whether people have checked radian versus degree. We're right now, we're just going to deal with degrees. I didn't discuss this, but I assume everyone knows that a circle has 360 degrees. You go all the way around. Half of the circle is 180 degrees. And of course, half that is a right angle. Perpendicular is 90 degrees. This is just a way of measuring angles. And we are going to learn about radians, and you may want to put your calculator into radian mode at some point, but you want to always know before you use it, because your sine, cosine, tangent, and your inverse functions are all tied into that choice. And if you use the wrong choice, you're going to get a number, and I'm going to look at it and go, right on the paper, obviously wrong mode. I check for things like that. All right, so just a little tech commercial here. I'll probably remind you this at some other point, but always check your calculator, see what mode it's in. So, all right, let's do it. Let's do a problem that requires a calculator. So we have a triangle with a hypotenuse of 10 and a side of 4. And we want to know what the angle is. Well, think of SOHCAHTOA. Cosine is adjacent over the hypotenuse. In our case, that's 4/10. So we know the cosine, we don't know the angle, but if you refer to your calculator, you'll note that the shift, the second shift of each of these functions is an inverse function. So we can say, what is second cosine 4 divided by 10? And I get 1.15. And why I got 1.15? It's the wrong answer. Don't know why. Anyone get 1.15? What did you get? Tell me. Somebody must have done this. Cosine inverse 4 over 10. What did I do wrong? I think I was told you a minute ago.
The radian?
Yeah, yeah.
You
Yeah, I left it in gradient mode. Oh, foolish. Okay, now I have to do it again. Cosine inverse 4 divided by 10. 66 point, A equals 66.42, blah, blah, blah. Now, knowing that, how can I figure out what this angle is? The other angle? Yes?
Since the triangle is equal to 180 degrees, so add the two angles that we know and subtract.
Okay, that's good. This is 90, this is 66, so I subtract from 180. It's also, they're complementary, so I could subtract this angle from 90, same thing. This side here, I actually have two ways to get it. I could use the sine function, right? I have the angle now, 66 point whatever. I could use a tangent function too, but there's another way to find it. Anyone see what that is? Just by looking. Oh. Geometry is a prerequisite. Let's try this one. You know the right triangle. 3, 4.
Can you do a squared plus b squared equals c squared?
I'm sorry, I just can't hear you.
Can you do a squared plus b squared equals c squared?
Yes. And what do you call that? You don't have to know.
I forgot.
It's the. Well, I can't remember. Pythagorean theorem. Pythagoras, Greek mathematician. This one actually is so common you should kind of know it. 9 plus 16 is 25. This is 5. 3, 4, 5, right triangle. All right. So we could do that here. We could say 100 minus 16 is 84, square root of 84. All right, anything else? If you look at my notes, you'll see